So with Spark 3.0, we've now added broad support for SQL. We've also integrated it with Python. And in some sense, it's really unifying now SQL analytics, or data warehousing, and data science. And that's really exciting because that's where we think the future is going. In fact, our customers were unifying these two things for a while. And actually, a pattern has emerged in which they call this the Lakehouse paradigm. So I want to talk a lot about that today. But before I dive into the details of the Lakehouse, I want to provide you some context of why we need it. So data warehouses were built 40 years ago, and they were purpose-built for BI reporting, and they worked really great for that. However, they don't have any support for video data, audio data, and text data, which is a lot of the kind of data that we have today. And as a result of that, it's very hard to do data science or machine learning on these data sets in the data warehouses. Also, they have limited support for real-time streaming, which is becoming increasingly important. And finally, they're closed and proprietary formats. So the data is either locked in a data warehouse, or you have to take it out if you want to operate on it with other tools. Therefore, today, most of the data is actually first stored in a data lake or a blob store, and a subset of it is moved into a data warehouse. So let's look at these data lakes. So the data lakes, they're great in that they can handle all your data now, and you can do data science and machine learning on it. However, they're bad at exactly the things that the data warehouses were good at. So they have really poor BI support. They're very complex to set up and configure. You need advanced data engineers to do that. And then once you start using them, if you try to do BI ever on a data lake, you're going to find out that the performance is really, really bad. Hence, as a result, what we're seeing is that a lot of these data lakes have turned into unreliable data swamps. And actually, most organizations, unfortunately, have to have both of these things side by side. So that is why we believe in the Lakehouse paradigm. The Lakehouse paradigm brings the best of both these worlds. You get the structure, you get the BI and reporting advantages of data warehouses, and you also get the data science, machine learning, AI, and real-time capabilities of data lakes on all of your data. In fact, the Lakehouse is distinct from data lakes. It actually starts out like a data lake, so it looks at the bottom layer like a data lake. But the crucial difference is that it has something that we call a structured transactional layer. This layer brings quality, structure, governance, and performance to data lakes. And at Databricks, we believe that open source Delta Lake project is a great way to get structural transactional layer on top of your data lake. So I'm going to talk a little bit about this next. So before I go into the details of the Delta Lake open source project, I want to tell you a little bit about its history and how it came about. So Delta Lakes are built on top of data lakes. And as we know, data lakes, they're great. They're really cheap. In fact, they have 10 nines of durability. They can scale infinitely. They also can store now all kinds of data, video, audio, text. You can also store structured, semi-structured, and unstructured data in these. And finally, they're based on open standardized formats. In recent years, we've seen in particular the Parquet format becoming the standard in this ecosystem, and lots of different tools can now directly operate on these Parquet files. So that's awesome. And as a result of this, organizations have now been promised that if they just build a data lake, they can get all these benefits. They can get real-time analytics, they can get data science, they can get machine learning, they can get data warehousing, reporting, BI, everything. So they've been very excited. They've built up these data lakes. Unfortunately, though, most of these projects are actually failing. And at Databricks, we started to actually see lots of demand for professional services. And we had to put our own solutions architect on these customers to look at what's the problem that they're facing. And what we did is we rank ordered the problems that we have to address with these customers. And I'm going to walk you through each of these problems. So there's 9 of them in the order of sort of severity that we saw. And then I'm going to talk about how we address them with the Delta Lake project. Okay. So the first problem that we actually noticed that is happening over and over again is actually a very trivial, simple problem. But it's actually that we were getting pulled in and customers were saying we have a hard time appending new data into the data lake while at the same time correctly reading it. Turned out some of the new data comes in. If you try to read it at the same time, because of eventual consistency, you might not see the results. So our solutions architects were creating copies of the data in different directories and switching it over when it was ready. Needless to say, this was really, really complex and costly. Second, Modification of existing data is really difficult with data lakes. And this is exacerbated when companies are trying to satisfy GDPR or CCPA. So in GDPR and CCPA, if a customer says, I don't want you to store any records in your data sets about me, you have to go and scrub those and delete those. Well, that's really hard with traditional data lakes because they're basically batch-oriented systems. So you have to run a big Spark job all over your data set once a week to scrub it to make it compliant. This was, again, extremely costly. Third, some of our customers were having problems that were hard to diagnose. After we looked into the logs and did diagnosis, it turns out that many years back, maybe some Spark job failed halfway through. Some of the data that it was ingesting had made it in, the rest was missing. And as a result, the whole project was failing. 4, real-time operations are really, really hard on data lakes. This is a special case of problem number 1, but mixing real-time streaming with batch led to inconsistencies. In particular, if you're appending new data in batch operation, but at the same time in real time you're trying to read it, you're gonna have problems. And this one is actually hard to solve. It's not just to copy files or copy directories. 5, organizations wanna keep historical versions of their data. Especially regulated environments, you have to reproduce your data sets because there's auditing and governance that happens. So here again, the poor man's version was keep copies of all your data sets in different directories with different date names. Very, very costly. 6, difficult to handle the metadata itself. Now, as these data lakes were growing, the data itself was growing into petabytes. The metadata for these systems was itself now becoming terabytes in size. And as a result of this, the catalogs that were storing the metadata were falling over, they were not scalable, so we were pulled in to do professional services again to fix that. 7, the too many files problems. Because data lakes were file-oriented, you could end up in a situation where you had millions of tiny files or a few gigantic files, again, leading to lots of problems when you were trying to consume it. 8, it was hard to get great performance. Because you're just dumping your data into the data lake without thinking about how it's going to be used later, how do you know if the data layout is sort of optimized for the performance that you need later? And finally, the most important problem, in my opinion, but a hard one to actually know, was data quality issues. It was constant headaches where customers would pull us in and it turns out that the data was changing in a subtle way or the semantics was changing over time or all of it wasn't there. So this was leading to all kinds of problems with these projects. So at Databricks, we wanted to take an opinionated approach. We said, we want to build a system that from the get-go tries to get all these things right so that we don't have to ever configure them or ever have to address these issues ever again. So the Delta Lake open source project addresses this by adding massive reliability, quality, and performance to your data lake. And the way it does it is by bringing the best of data warehousing and data lakes to one place together. And finally, it's based on open source Parquet format, so you can keep all your data on your data lake in this open source format with all these benefits. So how does it do this? So these were the 9 problems that I mentioned earlier, and I'm going to go through each of these and mention how we actually address this with the Delta project. Well, luckily, it actually turns out the first 5 problems can all be addressed with the same technique. By having a transaction log that stores all the operations that you're doing on your data lake, you can actually now make it fully atomic. That means that every operation that you do on your data lake either fully completes or it aborts and cleans up any residue, and you can try it later. The way that actually happens is that there is a Delta log, and it stores every operation. So for instance, here we have an example where one operation is adding 2 files, 2 Parquet files. They will atomically be added. Then after that, maybe that first file is deleted and a 3rd file is added. The key thing here is that Delta always makes sure that each of these are happening as if it was sequentially executed. Okay, so that's awesome. Now we can make sure that 1, if we're appending new data into the system, it's always either going to be there or it's going to be canceled, and you can read it at the same time. You won't have any issues. 2, modifying existing data if you want to get GDPR or CCPA compliance actually is really easy now because transactions enable you to do fine-grained upserts. So you can go in and modify small data in your data set in a transactional manner. Jobs failing midway, that also goes away because the job either fully succeeds or fully is aborted. And then real-time operations, it's the same thing. All operations, whether real-time or batch, are consistent with the transaction log. And now, finally, because we have all the deltas of all the operations that happened on your data set, we can actually implement something called time travel. Time travel lets you submit queries and then say, I want the answer to this as of the time 2 years ago. And it gives you the response as if the query was submitted 2 years ago. So this is great now for compliance and governance. Okay, so that's awesome. Now we solved those first 5 problems. How do we deal with the metadata problem? The fact that metadata is getting large and the catalogs are falling over. Well, luckily it turns out that there's a project called Apache Spark, and it's really, really good at large-scale parallel operations. So under the hood, we use Spark, and all our metadata is stored in Parquet format right next to the rest of your Parquet files. That way, you can actually move your data from one place to another by just copying the data. You don't have to worry about catalogs that are out of sync with the data that you have. So that's awesome. So okay, now we can scale the system with the Delta Lake project to really large metadata. What about the too many files problems? Well, the too many file problems and the performance problems that we're seeing with data lakes, we now automatically fix those because we automatically optimize the layout of your data. How do we do that? Well, a bunch of indexing techniques. 1, we partition, of course, your data. But 2, we also do data skipping. Data skipping enables you to prune the files based on statistics that you have on numerals. So you know exactly what's the max and the minimum of every data that you have in the files so that you can actually avoid reading a lot of the files when you get a query. And then finally, we have something called Z-ordering. Z-ordering actually enables you to optimize multiple columns at the same time. So if you have a year, month, date index, you now can actually search on just date, and it can be as fast as if you searched on year, which is hard with partitioning. Okay, so this is awesome. Now we get all these advantages that we had in data warehouses as it comes to performance. What about the last problem, the most important and the hardest problem, the quality issues? Well, it turns out that we can actually solve that with schema validation and evolution. So all data in Delta tables have to adhere to a strict schema. It can be a star schema, a snowflake schema. But as soon as you have the schema, we make sure that all your data 100% adheres to this schema. If any data appears that's not satisfying the schema that you have, we actually put it on the side in a quarantine that you can then look at, you can clean it up, and when you cleaned up the quarantine, the data makes it back into Delta. But now you know that all your data in a Delta table is always pristine. Okay? And finally, we've actually added something called Delta expectations. Delta expectations is a novel way in which you can actually express quality expressions using SQL or user-defined functions, UDFs, where you can specify pretty much any business logic for quality that you like. And now we guarantee that your table satisfies all those quality metrics always. And with expectations and schema validations, the pattern that we're seeing our customers use in data lakes is that they're actually now creating a curated data lake. The curated data lake now has bronze tables where you might have the raw data coming in, and then that gets refined into filtered, cleaned, and augmented tables that we call silver tables. And then finally, the most optimized business-level aggregated data sets are in so-called gold tables. And those are the ones that you're really sort of serving into your BI needs. So zooming out, the Delta Lake project solves the problems we had with the data lakes using 4 techniques. First, it uses ACID transactions. Second, it uses Spark under the hood to get the scale for the metadata. Third, it uses indexing and lots of different indexing techniques to get speedups that we traditionally used to have in data warehouses. And then finally, it uses schema validation and expectations to get the quality that we expect to have if we're using a data warehouse. We really want this to become the standard for how people create their lakehouses. So as a result of this, we've made this project work well with all these other systems. So you can now actually read and write both from Delta and Hive and Spark, Presto, Amazon Redshift, Amazon Athena, and Snowflake. And creating data with Delta is really easy. In SQL, instead of saying using Parquet, you just now in SQL say using Delta, and you're just using Delta. So with Delta Lake, we are able to fill in critical layer of the modern lakehouse architecture, bringing structure and reliability to your data lakes in support of any downstream data use case.